What specific problem does adaptive parallel decoding, APD, aim to solve in the context of large language models, LLMs?
Adaptive parallel decoding, APD, aims to address the challenge of balancing speed and quality in the text generation process of diffusion large language models, DLLMs. The core issue is that while DLLMs theoretically allow for parallel token generation, practical implementations often result in a significant drop in quality when multiple tokens are sampled simultaneously due to the neglect of inter-token dependencies. APD introduces a novel decoding algorithm that dynamically modulates the number of tokens generated in parallel, allowing for a more efficient sampling process that maintains high fidelity to the target text distribution. By leveraging a smaller autoregressive model to assess the quality of generated tokens, APD effectively reduces the trade-off between throughput and output quality, achieving higher generation speeds with minimal degradation in quality across various tasks. This approach ultimately positions APD as a significant advancement in enhancing the inference capabilities of DLLMs compared to traditional autoregressive methods.
How does the proposed adaptive parallel decoding APD algorithm work? Please illustrate it step by step, including the role of the diffusion model and the autoregressive model in this process.
The adaptive parallel decoding APD algorithm operates by leveraging both a diffusion model and a smaller autoregressive model to optimize the token generation process. First, the algorithm samples tokens from the diffusion model, P_D, in a left-to-right manner, which allows it to maintain autoregressive properties while generating tokens. Next, it uses the smaller autoregressive model, P_AR, to compute the likelihood of these sampled tokens in parallel, enabling the model to capture inter-token dependencies that the diffusion model alone cannot. The algorithm then defines a target distribution, P_T, based on a multiplicative mixture of the diffusion model and the autoregressive model, which helps determine how many tokens to accept based on their likelihoods. Finally, the algorithm dynamically adjusts the number of tokens sampled in parallel, balancing speed and quality by accepting tokens until the first disagreement occurs, thus optimizing throughput while minimizing quality degradation. This process allows APD to achieve higher generation speeds compared to traditional methods while maintaining competitive output quality.
Can you provide a simple example to illustrate the workings of APD? Walk through the main algorithm steps, explaining with this example.
To illustrate the workings of adaptive parallel decoding, APD, consider a scenario where we want to generate a sequence of tokens for a sentence using a diffusion language model, DLLM, like Dream7b. The main steps of the APD algorithm begin with the selection of a small autoregressive model, denoted as P_text_AR, which computes the likelihood of sequences in parallel. For instance, if we want to generate the tokens for the phrase, "the cat sat on the algorithm first samples from the diffusion model to get initial token candidates. Next, APD uses the multiplicative mixture of the diffusion model's marginal probabilities and the autoregressive model's joint probabilities to determine how many tokens to accept in parallel. If the diffusion model suggests the cat sat on the mat, the algorithm checks the likelihood of this sequence using P_text_AR. If the likelihood is sufficiently high, the tokens are accepted. Otherwise, the algorithm may adjust the number of tokens sampled in the next iteration. This process continues adaptively, allowing the algorithm to balance speed and quality by dynamically modulating the number of tokens generated in parallel based on the acceptance criteria derived from the target distribution, P_T. Thus, APD effectively accelerates the generation process while maintaining high fidelity to the target text distribution, as demonstrated in the empirical results of the paper.
What are the theoretical or practical benefits of using adaptive parallel decoding over traditional autoregressive sampling techniques?
Adaptive parallel decoding, APD, offers significant theoretical and practical benefits over traditional autoregressive sampling techniques. Theoretically, APD allows for the dynamic modulation of the number of tokens sampled in parallel, which mitigates the trade-off between speed and quality that is inherent in traditional methods. Practically, APD achieves substantially higher throughput compared to existing LLM decoding strategies, while incurring only minimal degradations in quality across various benchmark tasks. By leveraging a smaller autoregressive model to assess joint dependencies, APD can maintain generation quality even when generating multiple tokens simultaneously. Additionally, APD incorporates optimizations such as key-value caching and limits on masked input size, further enhancing computational efficiency and making it a more viable option for real-time applications compared to purely sequential autoregressive models.
How was the performance of the APD method validated or tested in the paper? What datasets and metrics were used to demonstrate the effectiveness of APD?
The performance of the adaptive parallel decoding (APD) method was validated through empirical experiments using the DREAM 7B diffusion model as P_TextD and the Quen 2.5.0/5B autoregressive model as HAT_TextAR. The effectiveness of APD was demonstrated on several benchmark datasets, specifically GSM-8K, GPQA, and Math, which are known for their math, science, and reasoning tasks. The evaluation metrics included accuracy on these tasks and throughput, measured as the number of tokens generated divided by generation time. The results showed that APD achieved significantly higher throughput compared to existing LLM decoding strategies, while incurring only minimal degradations in quality across these benchmarks. Additionally, the paper analyzed the trade-offs between speed and quality by varying three tunable parameters: the multiplicative mixture weight, R, the recompute KV window, W, and the maximum masked lookahead, M.
What are some limitations or drawbacks of the adaptive parallel decoding method as presented in your paper, and how might they impact its practical application?
The adaptive parallel decoding (APD) method, while offering significant improvements in throughput, has notable limitations that could impact its practical application. Firstly, the method relies on a smaller autoregressive model to evaluate the likelihood of sequences, which may not always accurately capture the joint dependencies between tokens, potentially leading to suboptimal generation quality. Additionally, the trade-offs between speed and quality are inherent. Increasing the multiplicative mixture weight, R, can enhance throughput but may degrade the quality of the generated text. Furthermore, the maximum masked lookahead, M, can significantly alter the output distribution, especially for complex reasoning tasks, which could hinder performance in scenarios requiring high accuracy. Lastly, while APD achieves higher acceptance rates for tokens, it still cannot fully eliminate the quality degradation associated with parallel sampling, which may limit its effectiveness in high-stakes applications where precision is critical.